Hello everyone and welcome back. So today, instead of doing a video on a particular topic, I thought I'd discuss a problem that I found pretty interesting. This problem, as you can see from the text in front of you or from the title of the video, seems pretty simple at first, but as you delve deeper into it, you find that it isn't actually as simple. So let's just try and draw the figure for this particular problem. Let's try and see what exactly this problem means here. So the problem reads, what is the minimum force required to pull a body on a rough surface? Now, when you see the term rough surface or smooth surface, this is just physics teachers' way of saying, teachers with an apostrophe, of saying that this surface either has friction or there's no friction. So if it's a rough surface, there is friction involved, and if it's a smooth surface, there's usually no friction involved. And when we talk about force, remember that force is a vector quantity. Direction matters. And you will see just why I chose to put emphasis on that particular statement. So let's begin by drawing our ground. So this is our ground over here. And I'm going to draw a body of mass m. Okay, so this is our body, this has mass m. And on this body, let's try and look at what all forces act, yeah? So due to Earth's gravity, there is a force of mg that acts on it, right? So we have that particular force. Then there is a force that is being acted on it by the ground. This force is the normal reaction. Although in this particular case, the normal reaction and mg have the same value, they are not necessarily equal, and they're also not action and reaction forces. This is because the reaction force of the weight of the object is the force that the object exerts on the earth, and the reaction force of the normal reaction is actually the force that the object exerts back on the ground. That is n again. But that's not necessary for our problem. That's just something that I thought was an important clarification. So that's that. And now what we have to do is these are the only two forces that are acting on the object at the moment. Now the question that arises is that when there is a force applied on it, there will be a frictional force that develops as a result of the body trying to stay at a state of rest, basically. So the question that arises is what force we need to apply in order to get this body to start moving. Now, the very intuitive answer, the very instinctive answer that almost everybody will come up with, even I did when I initially saw this problem, was to simply say, well, we apply a force F in this direction, there is a frictional force F that arises in this direction. So whenever this force F reaches the limiting value, the body will start to move, right? So we know that the limiting value of the frictional force Fl is equal to mu n, and so whenever this force is equal to, and which in our case is equal to mg, mu mg, whenever this is equal to F, the body starts to move, and hence this is the minimum force. But as we will soon see, this reasoning is completely wrong. And so what we have to do is we have to try and look and try and understand why this reasoning is actually wrong, yeah? So first of all, our statement what we've written over here saying that FL is equal to mu n is completely correct. But what if we found a way to make the normal reaction lesser? And then that's when the idea of force being a vector comes in. That is, instead of applying the force horizontally, why don't we try and apply a force at an angle? And that's where the main idea of that's what this problem really trying to test. But before I go into that particular case, let's draw the figure again and let's talk about why I didn't say, that is, let me just go down over here because the figure is down over here. Let's talk about why I chose not to say that the object was pushed and why I specifically said that the object is being pulled in this case, right? So consider the force F acting at an angle over here. I'm showing at an angle to illustrate what I'm trying to let's say that this angle is theta, right? This angle is theta, we have the force mg, and we have the normal reaction that is being exerted on this object over here. And then since the body is trying to move in this direction, there is also a force of frictional force that arises in this direction. So now let's try and resolve these forces into components and see why I chose to say pull and not push, right? So let's write the horizontal component. We can say F cos theta is the horizontal component Fx, and Fy is F sin theta. And now since this force is acting downwards, and since the object is in vertical equilibrium, we can write an equation for Newton's second law along the vertical direction. And since the net force along the vertical direction is 0, what we can write is F sin theta plus mg. Now these are the two forces that are acting downwards. And now we have to subtract the force that is acting upwards from over here. That is a normal reaction is equal to 0. And so what happens is that at the value of n in this case, when the force is a push and not a pull, is actually mg plus F sin theta. So the net normal reaction actually increases in this case. And moreover, since we are our aim is to decrease the frictional force, right? We want the frictional force to be as low as possible. In this case, the frictional force would actually be equal to mu mg plus F sin theta, which is actually greater than mu mg. Right, I've actually written it down over here. I forgot to scroll down. So as you can clearly see, it's greater than what we had in our previous case. So it's quite obvious that we shouldn't try and push, instead we should be trying to pull, because when we try and pull, this will become a minus, which I'll show in greater detail when I do. So let's draw this figure a third time and for the final time, right? And then we have an object of mass m over here again, and now we have the force F acting at an angle. Let's call this angle theta. My bad, this force is actually a pull, right? So it's acting away from the object, it's trying to pull the body. As a result, there are components on both sides. Over here we have an F sin theta, and over here we have F cos theta. And since the body is trying to be pulled in this direction, that is, it's trying to go in this direction, the frictional force actually acts in this direction. But that is not really relevant to our discussion over here. Also, the normal reaction is still acting upwards, so that's written over there, and then we have the weight of the object mg. Now in this case as well, we can write a equation for the normal reaction using Newton's second law. So we have n plus F sin theta is equal to mg. So what we get is that n is equal to mg minus F sin theta. So we have succeeded in our mission of lowering the magnitude of the normal reaction, but our job isn't over here, right? So from this we can write the expression for friction to be F is equal to mu into mg minus F sin theta. But so while we are minimizing friction, we also want to take care of another thing. We have to ensure that the body actually starts moving, right? So to ensure that, what you have to do is you have to write an equation for Newton's second law along the horizontal direction. That is, we need to ensure that F cos theta, that is the force that we are applying along the horizontal direction, is actually greater than the frictional force. And that is a second condition. So in this way, you can sort of imagine that there's a competition between the vertical component of the force and the horizontal component of the force. That is, we have to apply the force at an angle such that it sufficiently lowers the normal reaction, such that we have a low frictional force. But we also have to ensure that the horizontal component is large enough such that it is able to overcome the friction force. So when we have competing things like these, and it's usually best to involve calculus such that we're able to find the minima. Now in this case, what you're trying to find is the minimum force required, right? The minimum value of F. So using this equation that we can write for the horizontal direction, we'll get an expression for f. And now we'll probably have to differentiate that expression for f to get some value of theta for which this force is minimum. So let's write the equation over here. So we can write this to be f cos theta minus f is equal to 0, because we're looking at the case in which the body just starts to move. So we can basically consider the acceleration to be 0 at that point. Right, so this can further be written as f cos theta is equal to mu into mg minus f sine theta. And so in order to get an expression for f, we need to take this f sine theta within this bracket to the other side, such that we get f cos theta plus mu f sine theta is equal to mu mg, right? So then we can take the f common over here, and then what we'll get is I need a bracket over this, so I have to take it to the other side. We can write f to be equal to mu mg by cos theta plus mu sine theta. So this is our expression for f, but we are not done yet, because this just gives us a value of f in terms of the angle with respect to the horizontal, and that's not really useful to us, right? I mean, this is just a general expression for f. So what we need to do is we need to differentiate this expression with respect to theta in order to find the minimum of the of f, basically of the force f that we have to apply, such that we get a particular value of theta for which this force is minimum, and that for that value of theta we can substitute that add value of theta back into the equation for f, and then we can find the minimum value of f. So given that, let's try and differentiate this with respect to f. So let's do df, down over here, df by d theta. Now mu and b is a constant, so you can just keep it outside of it all. And since this is in the denominator, what we can do is we can write a minus of cos theta plus mu sine theta the whole square. I've taken the whole thing to be equal to like 1 by x form, and now I'll just differentiate this expression. So we have minus sine theta plus mu cos theta. So over here, while this expression looks complicated, remember that our job is to simply find the particular angle at which we require, basically the particular angle at which this expression is 0, right? So we can simply do this by setting this term over here equal to 0. So what you're going to do is mu cos theta minus sine theta is equal to 0. So we have mu is equal to tan theta, or theta is equal to tan inverse of mu. Now some of you who are familiar with friction know that this expression that we have found over here of theta actually occurs quite frequently, and well, this expression is nothing but the angle of repose or the angle of friction, and so you've seen that it occurs in yet another interesting way over here. Alright, so now that we have the value of tan theta, that is, we have tan theta being equal to mu, what we can do over here is we can find the value of the other two trigonometric components that we usually use, that is sine theta and cos theta. Now our reason for doing this will become apparent enough, but the thing is that we need to substitute this back into the expression, the values of sine theta and cos theta. Or actually we just need cos theta, as you will soon see. So let me just construct a triangle over here. So in this triangle, if I take mu to be one side and 1 to be this side, we'll find that tan theta for this particular angle will be equal to mu, right? And the hypotenuse can be found to be equal to 1 plus mu square. Of course, when you become adept at this, you don't actually need to create a triangle each time, but for the purpose of this video, I think a triangle would be really helpful, I think. So now that we have mu and 1 and root of mu square, we can write cos theta to be equal to 1 by root of 1 plus mu square. Now with this value, let's go back, and when I say theta over here, I don't mean the general angle theta. I mean, you can write this to be theta naught to denote the fact that this is the specific angle theta for which the force is minimum. So let's write that equation for theta, I mean for the force F again. So the force F that we had over here was mu mg into by cos theta plus mu sin theta, right? So let me write that again over here down. So mu mg by cos theta plus mu sin theta, and this can further be written as mu mg by cos theta into 1 plus mu tan theta. Because I didn't find the value of sin theta, I just drove cos theta from the expression and wrote it like this. So this we can substitute the value, so we'll find mu mg by cos theta is 1 by root of 1 plus mu square times 1 plus mu into mu. So this is nothing but mu mg by 1 plus mu square by root of 1 plus mu square. So as you can clearly see, we can just cut the denominator of this expression and give the root to this. So the final result, as it turns out, is actually equal to mu mg by root of 1 plus mu square. And I've forgotten to scroll down again. Yeah, but as you can see, this is the F min as required. And you can verify the fact that this is actually lower than the force that we've previously found out, because this expression over here will always be greater than 1, and the previous F that we found out was mu mg, right? And so we have this, so this can actually be written as F min is equal to F previous, if you want to call it, by root of 1 plus mu square. And since this value is always greater than 1, that is root of 1 plus mu square, F min is always going to be smaller than the force that we found out previously. So the minimum force that you need to pull a particular object isn't simply mu mg that you would get by pulling it horizontally, but it's actually mu mg by root of 1 plus mu square. And specifically, since the angle is important, since it's a vector quantity, we can specify the angle is theta is equal to tan inverse mu, which is commonly called the angle of repose, angle of friction, with respect to the horizontal, I guess. Yeah, with respect to the horizontal. So this is the entire question, or the problem, if you'd like to call it that. I had initially thought that this was going to be a short 10-minute video, but I've managed to drag this also to about like a 60-70 minute video. So I guess thanks for watching, and see you next time.